For our third talk, we have Herbert Spohn from TU Munich talking about coupled KPZ or stochastic Burgers equation.
Thank you very much. Thank you very much for this invitation. And I'm extremely happy to see that integrable probability is really flourishing. And well, about 10 years ago, I was with Jeremy at an interesting program at the Institute of Advanced Studies. And at that time, the KPZ fixed point, I mean, it was around, but you know, it was a dream. I mean, just nobody actually knew what that object was. It was just sort of appearing on your slides. I mean, there was the arrow going to the KPZ fixed point. And so I really, you know, I was very much impressed that you know, you just sort of insisted, and then you eventually, you know, after a lot of work, I mean, found out what is the true structure. So congratulations. Okay, so what I'm going to talk about is sort of these coupled Burgers equations. Actually, you know, it's sort of a minimal change. I mean, instead of having one component, let's just take two components, right? It will be not more than that. And I put here somewhat on purpose, I mean, this Burgers, because apparently, you know, the kind of tools, I mean, in terms of directed polymers and then the line ensembles and these kind of things, which we know from the single component case, you know, don't seem to, you know, I mean, don't seem to also continue to that point. So I'm mostly thinking sort of mentally, I'm thinking of you know, stochastic lattice gases or in the continuum version, which would be the stochastic Burgers equation. So this is joint work with the group in Bangalore, statistical physics group in Bangalore, and Kostya, I mean, who's somewhere in the audience here. He was actually visiting Munich, and he very much helped to develop this kind of things, which I'm telling you. Okay, so the first slide, you know, I sort of excuse myself, you know, it's something which everybody in this audience presumably knows. Nevertheless, I want to sort of put this, you know, so that you better understand what I want to do for the coupled case, you know, sort of mention some of the things and then, you know, have a common language and in particularly emphasizing the kind of observables which you are interested in. And so here you see the sort of, you know, the standard slide. I mean, so let's take the Dhar set. So particles are hopping to the right, and you know, say see a particle in front, then you know, it's simply blocked. And in this case, I mean, you're able to compute the stationary meshes, which are Bernoulli. And one interesting quantity, in fact, the one which I will mostly concentrate is what you know we usually call sort of a space-time correlator. So you know, this sort of relative to the invariant measure. And here, you know, I look at the occupation at time t at lattice ij and correlate it with the one at 0. And that defines for me the correlator as a function of space, which is discrete, and time, which of course is continued. And you know, when you look at large scales, I mean, you find this kind of scaling function, which has a typical exponent 2/3. And then there's a non-universal sort of non-universal quantity, which is sort of lateral gamma. I mean, this depends on the model, and of course, in case of the you can compute this explicitly, but maybe in other models it's sort of less explicit. Anyway, so there's this scaling function, which I like to call KPZ, because you know it's the correlator of the KPZ equation, and it's not a function which has some formulas, but essentially you should think of this like a Gaussian, it's sort of decaying a little bit faster, like e to the x cubed. All right, so this is one quantity which I would like to study in the two-component case. And the other one, which I will not emphasize so much, but you know, we also looked at that, and it's sort of an interesting additional information, is that okay, so for some reason we want to be always stationary, and then the correlator would be one, and the other sort of natural quantity is sort of the time integrated flux at some given point. I mean, so this is the time integrated current. And when you look at the space-time diagram, I mean, you realize that you have to sort of, you know, fix a direction in which you want to sort of compute the current. I mean, so this is sort of, you know, this direction here, I guess I denoted here by V. And if you look apart from the characteristic of your deterministic Burgers equation, I mean, then you will just see Gaussian sort of standard fluctuations. But when you go exactly along the characteristic, then you find anomalous fluctuations, which are governed by this by Green's distribution. You know, so the more precise statement is then sitting over here, right? I mean, there's a linear term, which sort of the law of large numbers, and then there's a fluctuation of order 1 to the 3rd. And there's again sort of a non-universal quantity, which depends on the particular model. And this by Green's distribution sort of skewed and has some non-zero mean. Anyways, This is the kind of thing which I now would like to do for the case of two components, right? Okay, so then the first model is two components. I mean, of course there are many other models than the Dhar set, and picking two components. I mean, you have a large variety of possibilities, and so let me give you one, because you see so far. Okay, so let me first tell you what the model is about, and you will see a little bit a posteriori. I mean, why I'm going to look exactly at that model, right? I mean, sort of this will come, but I cannot. If I tell you before, you will not understand what I'm doing. Okay, so here is now the two components. So this is an idea which goes back to Popov and Schütz, I mean, many years ago. And they were also interested in sort of doing two lanes, or to have two components. And they came up with the following sort of rather simple model. I mean, so you just take, rather than have the single lattice, you just take two lanes, right? I mean, just take a copy of the same lattice, and then I will have, besides the lattice, I lost my pointer here. Besides the lattice index, of course, I have now the index also of which lane I'm looking, right? I mean, so the points are labeled, so to speak, by the lattice, and alpha equal 1, 2. That's the label for the lane. Okay, and now these particles do something very simple. I mean, the top particles just do their path step, but all going to the right, and the bottom particles are going all to the left. So then I have just two independent path steps, and everybody in this room knows what to do, right? I mean, so that's, of course, not the problem. But now you want to sort of introduce some interaction between the two. And of course, you might think of particles jumping between two lanes, but no, you do something much more simple. I mean, you just say that particles stay in their own lane, but when they jump, I mean, they look at the other lane and sort of see what is the configuration there. And so I introduce this gamma. So if this particle wants to jump, for the Dhar step, it would have weight 1, but if it sees this particular configuration on lane 2, then it will have a different weight, which I shall call gamma. That's a parameter of my model, right? And for the other one, I do exactly the same. I mean, they all jump this way, and if they see exactly this configuration in lane 1, then it jumps with the weight gamma. So it's just sort of the mirror image. And that's it, okay? So that clearly induces for you some interaction. And of course, whenever you introduce some interaction, I mean, you don't know anything about the model anymore. But, the model what Schütz sort of computed, and the way how he constructed the model is that he discovered that, for that particular model, you can still compute what is the invariant measure. And the invariant measure is sort of, essentially Bernoulli. I'm very simple. I mean, sort of the sides are independent, but between the label, there's still some correlations, right? I mean, that's a very important fact of this model. Okay, so you think, okay, that's fine. I mean, so I can put some average densities. I mean, I can think of sort of stationary, and then I will put one density in the upper lane, one density on the lower line. So you have two conserved quantities. So if I look at the macroscopic equation, you will have a coupled hyperbolic conservation law, right? All right, so that's fine. And now, of course, you can sort of generalize the quantities which I mentioned before very quickly. I mean, so here, now the correlator becomes a 2x2 matrix. That's the obvious definition. So I have to subtract the average. And of course, if I look at that quantity at time t equals 0, then you see what I just told you. I mean, it's delta correlated with respect to the lattice index, but then there's a non-trivial static correlation. All right. And this, I'm not going to write formulas because it's more confusing, but of course, I mean, the matrix C alpha beta is known. I mean, it's some formula for it, right? Okay, and then now for the currents, of course, it's the same thing. I mean, you have to look in a particular direction, which you have to figure out somehow from the model. I mean, that's not yet determined. But then, this will be the time integral current will be some random 2 vector. All right, is the model fair enough? I mean, okay, and so you should only remember that when I take gamma equal to 1, that's the easy case. I mean, then things are just independent, and then I don't have to do anything. So it's gamma different from one which one is interested in. All right, fine. So now let's see what we can say. And one strategy is to not directly, of course, I mean, you might just think maybe I can find some integrable structure, so but that's I mean, certainly not known. And if you want to understand a little bit more about the model, I mean, it does make sense to actually look at the continuum approximation. I mean, so let me just sort of explain a little bit the continuum approximation. So here you have the deterministic, the two coupled conservation laws. And here I wrote out in full glory sort of, the second order expansion. And I use this Einstein summation convention. So, if you see here beta, beta, it just means that I'm summing beta equal 1, 2, right? And it's just sort of a little bit more transparent. And now you have the obvious terms. I mean, so, this is the linear term. I mean, then I have the quadratic term. And then I added by hand the diffusion and the noise term. Okay, so now the noise is here just sort of independent space-time white noise. Okay, and then so its strength is somewhat modified by this matrix B. So B, D, and H, I mean, these are all just numbers, right? I mean, or matrices if you want. So, but they're dynamical variables are the other phi's. All right. And now you see, I mentioned this flux Jacobian. So what the flux Jacobian is that it's just a derivative of the macroscope, the average current with respect to the densities. I mean, this is a 2x2 matrix, and this is what people call the flux Jacobian. Okay, so you have this A over here. That's sort of the leading term, if you want. So in this expansion, then you have the quadratic term, and you have all these things. All right. So now one thing which I studied many years ago is the case which sort of somehow the generic case. If you give me the model and you somehow fix what the densities are, then you will see what I call generic. The generic case is that this flux. Okay, so this matrix A here. I mean, this matrix A. I mean, there is sort of a very general property of this matrix. I mean, which sort of you can prove for many models and also for these models, is that A has real eigenvalues. It's always, essentially always a non-symmetric matrix, but it has left and right eigenvectors, and it has real eigenvalues. And the point, I mean, which I studied, which is the generic case, is that A has two distinct real eigenvalues. And then what that means is that you basically look at your linearized equations. It's just this little thing over here. These are sort of, to speak, linearized Euler equations, and the solution of these linearized Euler equations tells you that you have simply two, if you make a little excitation at the origin, I mean, you have simply two sort of peaks which are sort of moving out, right? I mean, on the Euler scale, these are exact delta peaks. I mean, it's just a simple solution of that equation. But then if you add noise and all these nonlinear terms, then you will see some broadening. But the main point is that they separate in time. And for a long, if you wait for a very long time, they're very far apart. And then you argue. I mean, nobody has ever proved that, but I think it's just we don't have the tools, but it's certainly true that they simply decouple into two scalar Burgers equations. Now, of course, there are exceptions. I mean, it's not always true. There's a somewhat more complicated phase diagram. So there's this work by Gunther, I mean, who looked at more sort of more components, and then you find this Fibonacci sequence of dynamical exponents. Anyway, so this is not important for me. The main point, what I want to say, is that in case this matrix A, I mean, the flux Jacobian, has two distinct eigenvalues, I'm not saying that we can prove very much, but we really know more or less what's going on, and it's reasonably well confirmed through sort of numerical simulations. But now, and it's the case which I remember, I was always sort of worried about, is that what happens if actually, the A is degenerate, and if it's degenerate, I mean, then they have the same eigenvalue, and so then of course I can just put them equal to 0. So the question is, what happens if A is equal to 0? That's really the thing which I would like to explain to you. Okay. All right, so this is why I call the title degenerate flux Jacobian. I'm looking at a very specific case where this leading term happens to be 0. And now you see that the problem is really much more difficult because both, I mean, peaks are just standing still, and they have a lot of time to interact, and so this idea of decoupling, I mean, it's just sort of a total, this is certainly not the right idea. Okay, so the next point is that. Why bother? I mean, why do I even want to study this, right? Okay, so let me explain you that there is actually an interesting motivation, and it comes from an observation which was sort of maybe it's already 4 years back, but in this sort of condensed matter community, which are studying this one-dimensional system, it was a big splash. I mean, people were really excited, and lots of literature. I mean, the people do simulations. I mean, whatever. There's the Google group who are developing quantum computers, which simulation, which have 100 authors. Anyways, so this is a big place. So let me just sort of explain you in my own words. I mean, what they found. I mean, so you look at the isotropic Heisenberg model that's up here. So this is now quantum mechanics. I mean, so these are just sort of a Pauli spin sitting at each lattice side, and then you have this quadratic interaction. So that's the isotropic Heisenberg model. Or you can also look. I mean, this is an integrable system, and you can also look at the sort of the classical analog. In which case, I mean, you have three vectors which are sitting on the unit sphere. And if I just copy this one up here, I mean, that's actually non-integrable. But this was done many years ago. And people sort of observed that when I take the log of 1 plus the scalar product, then it's again an integrable system. Okay. And now what people basically found through simulations is that this spin correlation function. So this average is now let's say a high temperature state. I mean, you can say it's quantum mechanics, you just think of the unit matrix. I mean, so every state is sort of equally likely. I mean, that's infinite temperature. Or in the case of the classical model, you can think that the initial measure is just a uniform measure on each sphere, right? I mean, so these are very simple initial conditions. And then you do exactly the same thing. I mean, you average, it is now deterministic, so you write on your, you solve your equations of motion, and then you have random initial data, and this is over what you average, right? And then what you seem to observe numerically is that it really goes like the KPZ scaling function, in particular has a 2/3 scaling exponent. All right, so let me show you. I'll explain this in a second, but let me show you sort of the numerical evidences of this. So I put three slides here. So one is actually from our group. I mean in Bangalore. So here, you see that the green line is the Gaussian one, and the other one is sort of the numerical data. And so you see it falls off a little bit faster, and then I mean the KPZ function sort of looks like a better approximation. You see here we are down to 10 to the minus 4 already. Okay, of course, there are imprecisions, and it's numerical, right? But I mean, at least it's clearly non-Gaussian, and most likely. But the scaling is pretty perfect, right? I mean, this is already the scale data. And now here you have sort of two quantum simulations. I don't want to say much about this one up here. Up here, I don't want to say, but I want to say one word about this thing because this might be interesting for this audience here. So this simulation is actually the 6-vertex model. Right? So you look at the transfer. I think they do look at the diagonal transfer matrix of the 6-vertex model. But now you see you want to have the time evolution be unitary. But now if you look at the 6-matrix model, of course it's not another unit. It's a transfer matrix, so it's certainly not unitary, right? Essentially, exponential of some symmetric matrix, right? But now you do an analytic continuation, and you actually achieve and sort of putting the matrix weights in such a way that the transfer matrix is actually unitary. And then they simulate that unitary matrix. So integrability is very important, and this sort of seems to give sort of the most convincing results. I mean, here you see that it can go almost down to the 10 to the minus 5. I mean, and you see exactly that. Anyway, so this is the observation. And now, people sort of try to do approximate series and explain this. I mean, there's still sort of question. I mean, is it really KPZ or only approximately? And anyway, so there's a lot of discussion. And then there's sort of one recent paper by Jacobian, and he sort of proposed like a two-component Burgers equation. That was sort of the reason why I wanted to study this case. And he has a very specific case, namely his two components. Here you have just this phi1, phi2 coupling, and here you have the y phi1 and phi2 squared. Right? I mean, it's a very explicit sort of, and then he's claimed that it's sort of KPZ-like. And anyway, so now you look a little bit more carefully at this thing, and then you realize that if I take lambda equal to 1. Then you can do a rotation by pi over 4. I mean, just rotate by 45 degrees. And then you see that the two equations do decouple. I mean, so you see that lambda equal, it's just like our gamma equal to 1. If I put here lambda equal to 1, then I just find two independent decoupled Burgers equations. But it tells you also something which took me a while to understand, and Kostya also insisted always on this point. You see, you might think that these are coupled, but when you do a rotation, they are uncoupled. And so, there's always sort of this rotational degree of freedom which you have to keep in your mind. Okay, so that's something which does not appear for a single component. All right, so now what I want to tell you a little bit more about what we can say, but I just emphasized already that we always use this kind of normalization, and later on I will show you sort of simulations for the case lambda equal to 0 and lambda equal to -1. Okay, so now we have to get a little bit more deeply into the subject, and one question which of course was mentioned already many times here. I give you a model, and if you don't know anything about the invariant measure, I mean, maybe you close your book, or maybe you think about something sort of whatever. Now, other methods which might be accessible, but of course, I mean, here we are using the fact, and I very heavily want to use the fact that we know something about the invariant measure. Okay, and so now I just have to remind you of what the equations are. I mean, I put A equal to 0. H I've sort of relabeled as G because that's what we're using, and this is the equation which we want to look at. But now comes the important point, is that so this is sort of the linear part of our equation, and of that of course you know everything. And so when I look at the static covariance, it's a solution of that particular equation. And now what I want to say is that in the following, I will always sort of normalize the fields in such a way that this C is actually the identity matrix. You see, if it's not the identity matrix, then you have to multiply this field to get some coefficient, and it can transform it to that case. But the point is, so the idea is, I want to, you see, I mean, the question is, what is sort of the comparison, so to speak? And if I look at two models which have different C's, I mean, then I cannot compare, because then locally they will have different invariant measures. And so rather, if I want to do the comparison, I first make sure that locally they look the same. And that means that I always have to put C equal to 1, right? And if it doesn't happen to be equal to 1, then okay. All right. So the next main point is that I discovered quite some time ago that if you require these two matrices, I mean the G matrix, to be cyclic, I mean now they call it trilinear, but I call it cyclic. So let me keep my notation. Then actually you know that what you know already from the one-component Burgers equation, namely that the product, that the space. The independent space-wide noise is actually an invariant measure for that system. And there has been subsequent work by I mean, in particular, I mean, Kulkarni studied this, in great care, and then all the things that I'm saying here, that they are actually theorems. So I don't want to give the general definition. I just want to insist that this condition is also it's under the assumption that I have done already the transformation such that C is the static correlator is already the unit matrix. And then these matrices which actually have this property, this is why it's a cyclic structure. I mean, you see that the B is here, the diagonal, and then it appears over here, and the C is sort of at the lower bottom, and then it appears as sort of in the off diagonal. So this is why I called it cyclic. Anyway, so the theorem is that, and it's sort of more or less the same argument as you do for the one-dimensional case. I mean, you first you first fix a linear term so that C is equal to 1, and then you realize that when you add this, I mean, this measure stays invariant. Okay. Now that's of course I mean, I have many parameters, but that's a subset which I'm looking at, and okay. Beyond that subset, we know essentially, I mean, essentially nothing. But what is important to me, the example of Jacobo actually satisfies this condition. I mean, if you go back to his equation, which I can do for a second here. So if you go back to this equation, I mean, you can figure out what, you have these coefficients, and then you see that A is equal to 0, B1, C 0, and B equal to lambda. So that's fine. All right, so we are covering sort of the cases of actual interest, right? But I think it's useful to have this somewhat larger class of things. So I'm going to use time. Okay. All right. So now let me see what I can do. Okay. So here comes sort of the universality class. Let me forget about the current. And so I'm just stating a statement about sort of what we believe is sort of the universality. I mean, so here I'm just saying that okay. Generically, the usual scaling argument we should do, I mean, for the 1 to 2 scaling will not be sensitive to whether it's sort of a vector or scalar. So we believe that there will be always a 2 to the third, but then of course there's a scaling function on which we don't know, and of course there will be exceptions which you can find in our paper. And so the conjecture is actually that within this class of cyclic matrices, the classes are defined by gamma. That's a universal time scale. That's just like in the one-dimensional case. But then on top of this, you will have the rotation, right? So when you look at the rotated equations of motion, then the space-time correlator will be just simply rotated as a matrix. And then, of course, one would say that they're in the same class. But otherwise, the idea is that they're actually changing. And if you want to have a comparison, then I'm thinking of like let's say something like random matrices. Let's say like the beta ensemble, and I look at the largest eigenvalue, then of course you always get the 1/3 exponent. But when you look at the actual distribution of that eigenvalue, it will depend on beta. And that's the picture which we have here, right? I mean, so the 2/3 exponent, except for obvious exceptions, is always correct. But then the scaling function will depend in a way which we don't know. Will be sort of labeled by will be labeled by these cyclic matrices, and they fall into classes given by the gamma and the I, right? So the cyclic matrices are actually invariant under these rotations, and of course because we choose the unit matrix, also the invariant meshes are invariant under this and under these two operations. Okay, so now let me go back to the two-lane model and try to see what we can do. And then the reason why we picked the two-lane model in the first place is that if I, so to speak, are at half filling, so I put the top layer density 1/2 and the lower layer also density 1/2. It so happens that I mean the flux Jacobian is really exactly equal to 0. So if I'm off this point, I mean then I see the two peaks, and then I can sort of use the old theory. But if I'm exactly at this point, I mean then I find that the flux Jacobian is actually 0, right? Okay, but now you see I emphasize that when you do the exact solution, then the C matrix is still a non-trivial 2x2 matrix. So I have to do this operation. I have to, first have to rotate. I mean, then I will make it diagonal, but then I have two different eigenvalues, and then I have to rescale the field so that the eigenvalues will be sort of then 1, right? I mean, and so then you do this little computation, and what you discover is that when you look at this continuum approximation, it's exactly of the form of what we found, what Jacobo was sort of proposing already, right? I mean, so it has exactly the form which is sitting over here, which has cyclic matrices and sort of coincides with the one which Jacobo had. Okay, so that was very nice because rather than trying to simulate the continuum equation, which might be difficult, I mean, you also might want to simulate this lattice gas, which is sort of a totally different simulation, so you can sort of compare and have some sort of somewhat safer background. Anyway, there are two symmetries which I want to mention here. One symmetry is that the two-lane model has a particle-hole symmetry. So if I interchange occupied and empty sites, then this just amounts to interchanging 1 and 2. And so from this you find that the S11 has to be equal to, I mean, pointwise, it has to be equal to S22, and the off-diagonal terms have to be also equal. Right? Whereas for the Burgers, I mean, in probability, you see that when you look at your equation, you see that with this initial data, I mean, then you see that the phi1 is equal to minus phi1. And then from this, it follows that the S12 and the S21 has to be exactly equal to 0, right? Okay. And then another thing which you can do, which I'm not going to go into, is the mode coupling. And the mode coupling tells you a strange result. I mean, first I didn't believe, then I need to redo it again. But that's just what mode coupling tells you, that the S12 is actually even in lambda. So in particular, it would say that it's even when lambda is equal to 1 and lambda is equal to -1. Okay. Now the other thing which I haven't pointed out yet is that there's this lambda, and of course the two-lane model. I had the gamma, and then you see that the gamma equal to 1. I mean, then of course that corresponds to the decoupled case where lambda is equal to 1. But you can vary gamma, but of course it has to be positive, otherwise it's not a probabilistic model. And so you see that you can reach all the negative values of lambda. I mean, and we pick lambda equal to 1.4 because somehow we thought that that's furthest away from the decoupled case. I mean, in a rather vague sense. But anyway, but you can reach all the negative thing, and then this identity is sort of very mysterious, because it would say that the correlator of the lattice gas where the gamma is actually rather small, it's sort of the same as at the decoupling point, which of course doesn't make any sense, right? I mean, if you think about the lattice gas, it just cannot be. But okay, I will show you what it is.
Not in any doubt.
You're
not in any doubt about the
well, okay, no, well, I mean, on the level of mode coupling, I think it's an identity, right? I mean, but of course, mode coupling might be very bad if I'm very far away, right? I mean, that sort of was our original explanation. Yeah, no, sure. I mean, mode coupling, then we sort of first draft of the paper, we argued that it's only true for lambda close to lambda equal 1. Anyway. Okay, you will see what's right. Okay, so now the task is I guess pretty. How much time do I have? I mean, yeah, okay, that's just fine. Okay, so now the task will be actually rather simple. But what I want to do is so we don't know to prove any theorem. I mean that you discovered already. But I want to show you at least sort of some support of what is the picture which I was trying to develop. So first I want to show you the coupled Burgers equation at lambda, just at lambda equal to 0. So we just have 1 point away from the decoupled one, and then one thing which I like very much, I want to show you in what sense there's universality, in the sense that what we find for Burgers is really the same as what we find for the two-lane. And that's a somewhat non-trivial observation. I mean, and anyways, so you will see. And okay, so anyways, yeah, maybe I should explain this in 2 words more. You see, what I mean, the point is that if I just say, okay, so let me first show the pictures, and then I can do some more explanations. Okay, so this is now the continuum equation, right? So we only have we have only 2 components, and because the off-diagonal terms are exactly equal to 0. And what you should see is that first of all that this peak is sort of this is slim and rather high. I mean, you see this is 0.3 and this is 0.15. I mean, so this is sort of the fat guy, and this one is the slim guy. Physically, it's this one which Jacob was actually interested in. And so our argument, so this yellow line is sort of the one is the KPZ function. So we do it at lambda equal to 0, right? I mean, so we argue that you see here it's sort of not really KPZ-like, and also it's somehow too fat on the top. And so from this we argue that the scaling function changes. I mean, not dramatically, but it changes. Okay. And this is the other one here. The fit is sort of much better actually to the KPZ, but physically it's the one component which is the relevant one. I mean, for reasons which Jacobo has to explain to you. I mean, it's just sort of the way how that's part of his approximation. All right, so the first thing is that this picture that we have the scaling exponent 2/3, but then the scaling function changing as we change the parameters. I mean, that sort of, it's not too much of evidence. I would like to have more, but this is all what I can show you. Okay, now I show you the one for the lattice gas. So first of all, there's the symmetry. I mean, you know, this one and this one is the same, and also the off diagonal. And now you will say, you know, this is way above any KPC type thing. But now you see that it's important that we do the correct comparison. You know, here it's just sort of, you know, we took as 1 and 2 component, just sort of lane 1 and lane 2, as you would do naively. But that has no reason to be equal to what we see in the continuum, because you have to do this rotation. And so what we did is that we just take the data the way they come out of the computer, and then we do this rotation and rescaling. Okay. And then, okay, and the way the next one which I show you is that we take sort of as our comparison the numerical solution of the continuum equation, and then we compare it to the rotated and dilated data from the lattice gas. Well, these are the four matrix elements of your static correlator, of your dynamical correlator, right? I mean, it's a 2x2 matrix, which has 4 entries, right? And a priori, there's no particular symmetry, but we have the symmetry. So you know, it's sort of useful to check that the numerics works well. I mean, you know, to actually record both of them, right? Because you do it, you know, configuration by configuration, and then the identity, of course, is on average, right? And then so. Okay, so this is why we have 4 pictures, right? Okay, so now let me show you this one here. Okay, so first you should look at the top one, and so you see that you know, the underlying red line, which you can hardly see, is the one from the continuum equations, and the blue dots are the data from the lattice gas at different times. And so you see that they really, I mean, you know, to my taste, I mean, what you see, I mean, they just perfectly matched. And of course, they match only because we did the right rotation. You know, it's something which you really have to do on the level of this model. I mean, otherwise, you know, if you wouldn't, you know. And the only thing which we do here as a free parameter is that, you know, we still have this coefficient. Well, I mean, we have a coefficient gamma here, sort of which we cannot directly determine from the computation, and so you should think of this sort of like a 1 parameter fit, but you know, this then works very perfectly. Okay. All right, so this is sort of just confirming that the 2 models are in the same universality class. And the second thing which I wanted to show you is sort of this lambda equal to -1, and this is sort of what you find. So it's very surprising, because you see now that this, so this is again, you know, 1, 1 and 2, 2. I mean, so the off diagonal, you know, R0, this is a continuum model. And you see that now the 2 peaks are actually the same. I mean, just as you would expect for the, you know, the fact when you do it at lambda equal +1, because they are decoupled and it's just the same. But here, okay, you see, again, yeah, it doesn't quite fit, but you know, many features, you know, sort of seem to be okay. And the level of the lattice gas, it looks a little bit strange, but you know, this 2-lane model. But you know, because I mean, if we make gamma small, you know, gamma minus, I mean, -1 means, you know, gamma very close to 0. So you know, you see a lot of blocking. But anyway, so this is what you see. Okay, so I think this sort of brings me already to the end, and I just want to close with the kind of things which I said. So first of all, you know, we looked at the degenerate flux Jacobian. There are no normal modes anymore. You know, I mean, the eigenvalues, eigenvectors of this matrix are sort of not very useful. So we looked only at the cyclic class, and the scaling exponents, you know, very limited data seems to be so well confirmed. I mean, the t to the 1/3 comes when we look at the Bike-Wayne distribution, which I didn't show you, and the real new element going from the scalar to the vector case is really, you know, the role of these rotations, which is a little bit mysterious, but you know, it's clear that you have to take this into account. Okay, and sort of one thing which sort of I mean would be interesting. Of course, we don't know anything beyond cyclicity, right? And it's actually not very clear to me. I mean, it could very well be that if I go beyond the cyclicity class, I mean, you find stationary measures which are not short-ranged. And if we would find such a situation, then of course, you know, the whole pictures, I mean, you know, the sort of this naive scaling picture breaks down completely. And then of course you could find different dynamical exponents, but we simply don't know. I mean, there's a very early paper by Dhar in Erdős, I mean, who looked at this thing, and but this was at the time when the computers were extremely primitive compared to our modern standards. So it's not clear how reliable the data are. So we somehow try to redo them. And anyway, thank you very much for listening.
Questions? Can you think of a clear situation happening for the case of anharmonic chain?
No, for anharmonic chains, there's essentially, there's a theorem basically that the speed of sound is non-zero. And then you see that then you have three modes, and one is anyhow sort of, the heat mode is just standing still. Okay. But since Tomohiro is asking this question, I wanted to mention this. I mean, there's one very beautiful result actually by Yannick here and Tomohiro Sasamoto, which looks at the two-component case, but he looks at, what we would call step initial conditions, right? And they have results actually on the integrated current. I think that's sort of one of the few mathematical results which we actually have in this area. Of course, I mean, I also didn't mention Amol. I mean, Amol talked about, I guess on Monday also, he talked about two components, several components. You had these colors, I mean, which of course special cases of two-component systems, right? But I don't think they show anything of this type of feature, right? I mean, I think your flux Jacobian is always different from zero. I mean, that's at least what I would have imagined. I mean.
Yeah, I should ask you about.
Okay. but I think so. I mean, yeah. Well, but you just have to write down your hydrodynamic equations, which you don't know really. Okay. All right. Anyway, so I just want to mention that, that there is work. I couldn't mention any names because of time, but yeah. Mm-hmm.
The kind of the fitting in KPZ the page
What are you referring to? What
one of the pictures.
Oh, one of the pictures. Okay, so let's go back. You're referring to this picture? Well.
Yeah, does mean that the scaling should be changed?
No. I see. What I'm trying to say is that you see, I mean, everything is scaled already with c to the 2/3, right? I mean, so when I look at this picture.
Not this one, not on the screen.
Well, okay, so you were looking at this one?
Yeah.
Well, I mean, okay, so it's always plotted already on the scale t to the 2/3. So these curves, of course, they're not absolutely perfect, but I mean, sort of by usual standards, I mean, would say that have a good scaling. Right? I mean, in the sense that they really lie on top of each other. If we plot them, there's no these are sort of raw data. I mean, there's no maneuvering, so to speak. I mean, you just take the data. But you plot it on the scale t to the 2/3. I mean, your times should be not too short, and then they sort of lie really on top of each other. I mean, up to numerical errors. I mean, this is the kind of quality which people can produce, right? I mean, if they make very substantial more efforts, and maybe they can produce a little bit better. But anyway, I mean, that's sort of the kind of thing. Okay? So from this you basically learn that the 2/3. Which would be very surprising if the 2/3 would not come out, right? I mean, this would be sort of, real mystery, right? I mean, but it's all related to the fact that just like in the one component case, we know that the Burgers equation, this coupled Burgers equation have, white noise as spatial white noise is stationary in nature.
Yeah, question. Okay, now let's say. Let's start next talking maybe 1 or 2 minutes.